Thank you for tuning in to Logan Mayer Walford's Chapter 6, Problem 2, Video Explanation. So, coming over to this Word document where the problem can be found, a 20 kilogram traffic light is suspended with two cables. Draw a free body diagram and find the tension in each cable. Now, the free body diagram is over here, and there are a couple really important things to note about this diagram first, before we even look at this. First, the angle is the same. The only way that could happen is if these ropes were the same length. So they have the same angle and the same magnitude, or same distance, meaning that the tension on each of these ropes is going to be equal. Important thing to note for later on. Now moving over here, we can notice that I have 53 degrees and 37 here. Well, how did I get there? Simple. 37 plus 37 my bad. 180 degrees, the sum of all interior angles in a triangle, minus 37 is equal to 106. This big angle right here. But I don't want that angle. That's not very useful to me while I'm doing my calculations. So instead, I cut it in half along the y-axis, and I get 53 degrees and 53 degrees. Much simpler thing. Measurements to work with, I should say. Now, we make sure that our tensions are equal distance and roughly equal angles. Unfortunately, OneNote nor Word has a compass, meaning I can't superimpose a circle on there to make sure that they're perfect, but it is the best I can get with the naked eye. And we just simply label them T. Some people would label them T1 and T2, but the only difference in these is direction. But there's a interesting rule with vectors. If it has the same degree off of an x-axis and the same magnitude, it doesn't matter where I put that vector, it's the same thing. Now, keeping that in mind, I just need to write vector t to denote the vector. And of course, we have the always present force of gravity, which is denoted with a straight down arrow in the y-axis, because last time I checked, gravity was still pulling me straight down towards the center of the Earth. Be a little odd if it started pulling in the other direction. Might have to go talk to the NASA people if that happens. So, that is our answer for problem A. We can box this, call it a day. Now, for B, we need to use a little bit more math. We're asked to find the tension. Now, the tension in a cable is equal to its hypotenuse length for the vector, which, thankfully, we know how to find using a combination of trigonometry and Newton's second law. Newton's second law is force equals mass times acceleration. Now, we know the traffic light isn't accelerating, so that's 0. But we also know that there's forces being applied to it. So, instead, its force net is equal to mass times acceleration, and the force net is equal to 0. But our force net can be broken into components, which is what we must do in order to solve this. Starting with the simpler side first, force net in the x direction. Now the reason why this is simpler is A, there's only 2 vectors instead of 3, and B, those vectors are the exact same, just in opposite directions. So if we have an equal magnitude, equal angles, just exact opposite of each other, tx minus tx is 0, which matches with the diagram. Simple. Now for the y. This is where it gets a little more tricky because we have to take into account gravity. And our forces for ty going the same direction. Meaning instead of 1 just setting opposite to each other, we have to multiply them together. Or, more accurately, multiply ty times 2 and add them together. So, if the f net of y is 0, because once again, our light isn't going to space, and it's also not going towards the center of the Earth, it's just hanging there, it has to be 0. And if f net y is equal to the tension of y times 2 minus the force of gravity pulling straight down, because gravity doesn't move it side to side, only down, then we know that 0 is equal to ty times 2 minus 196 newtons. We derive that from this equation. The force of gravity is equal to mass of the object times the gravitational constant, which is 9.80, to give us 196 newtons. That only works if the mass is in kilograms. Now, in order to find how I transform ty to t cosine of 53, we have to go back up here. And we have to look at these guys. My laws for cosine and sine. Now, if, when in trig, I wanted to find the length of a side of a triangle, knowing the length of the hypotenuse and an angle, an interior angle, I simply looked at it, okay, is it opposite to whatever angle I'm studying or adjacent? In this case, ty, which is this right here, the height of the triangle, the height of the vector, is cosine. It's adjacent to this angle. So cosine of theta is equal to adjacent over hypotenuse. Well, that's not very helpful. I'd have two variables. Not useful. So instead, I isolate my adjacent side. Adjacent is equal to the cosine of theta times the hypotenuse, or t, that magical number I need. So suddenly I go from an equation that has nothing I need to an equation that has one variable from one equation, and best of all, it's the variable I needed. So substituting in for here, and once again I have that written up here, ty equals t cosine of 53, I get 0 equals t cosine of 53 times 2 minus 196 newtons. Remember, force of gravity. Isolating for t, I get 196 newtons is equal to 2 times t times cosine of 53. Isolate for t once again, and I get 196 newtons over 2 times cosine of 53, which is equal to t, which, when I do the math, is equal to 162.84 newtons. I hope you have enjoyed and understood this problem, and realize that if we stop, take our time, break stuff down into its simplest parts, which is what physics is all about, even the scariest of problems sometimes turn out to be a little more than kittens dressed up. Hope to see you again soon. Goodbye.